So, now we are going to look at the thermal destruction kinetics or food safety kinetics. So, when you are processing food, you always kind of interested to know how safe it is. So, I mentioned milk is processed at 72 degrees Celsius for 15 seconds. How do you select that 72 Celsius? How do you select that 15 seconds? When you are processing canned food, for example, maybe you are processing canned foods at 121 Celsius for 30 minutes. Why 121 Celsius? Why 30 minutes? Why not 15 minutes or why not 45 minutes? To understand some of these questions, you need to understand the bacteriology or thermal bacteriology, because every raw product contains bacteria, and not all the bacteria is going to be harmful. There are beneficial bacteria. So, we talked earlier in the morning probiotics. They are talking about bacteria present in yogurt and number of the fermented products. So, those are all beneficial bacteria. We are not talking about those bacteria here. We are talking about pathogen. Those cause diseases to people, and also spoilage. Those spoil the food. And so, that is kind of what we are trying to understand here. To understand that, we need to know how bacteria die when you are heat treating it. So, the bacteria are basically going to look at a logarithmic order of death when they are heat processing it. What that means is you are going to have so many bacteria, then you process at say 70 Celsius for 10 minutes, you are going to reduce, let us say you have 1 million bacteria. In 1 minute you may reduce to say 10 power 5, and then second minute it may reduce to 10 power 4, and so on. And then you kind of keep plotting, you get something like this. So, you have initially certain bacteria, and then with 10 minutes you are going to reduce this, and so on. And then you get a plot this, you get a curve, and then you want to find out how much time it takes to reduce the population by 90%. So, from say 10,000 to 1,000. So, that's your called the D value. So, this is kind of happens, the heating is going to basically it is a heating time, how much time you are heating the food at constant temperature. It is much easier to do in the lab environment, because in the lab you can maintain temperature everything constant, whereas when you do in the industrial scale it is much more challenging. So, that's something we will probably talk later. So, the concept D value basically is the time required to reduce the population by 1 log or 90%. So, if you use mathematically, what is the time to reduce the population by certain percentage? So, this is going to vary for each microorganism, and for example, there may be microorganism takes longer at a certain temperature, whereas some microorganism may be easy to inactivate, and so on. So, when the D value is larger, it takes longer time to process. So, that means they are more resistant to heat. So, when you look at different technologies, like for example heat versus radiation versus pressure treatment and so on, we will see that there is no correlation between pressure resistant to heat resistant to radiation resistance and so on. So, you need to understand that. So, a bacteria may be more temperature resistant, but may be easy to inactivate by pressure and so on. So, you have to get understanding of all those things. So, when you do this D value calculation, you are going to assume certain parameters. In engineering, we make a lot of assumptions, and then we are going to derive some mathematical relationship, and your mathematical calculations, the strength of that depends on the assumptions you make, And a lot of times some of those assumptions, when you deviate, then those calculations are only estimate but not necessarily accurate. So one of the first assumption is all the population have the same resistance. So what we are saying is, in this room maybe we have 50 people. We say all the 50 people behave the same way. We know that's not true. Each of us have unique characteristics. The same way, microorganisms, there may be millions of them. Each one has its own characteristics, and so there may be some difference in microbial resistance. Second, if you have done microbiology, plating, other techniques, you probably might have counted colonies and so on. We assume that you are counting each colony in a plate. You can say that this is from one colony is one microorganism and so on. But it's possible that this one colony may have a cluster of 10 microorganisms, but you are kind of counting that as one colony. So again, we assume there's no clumping. And then there's no heat activation for spores. So that means a spore remains as a spore, and there's no injury. So injury is basically when you're heat treating it. You can say, if those of you who are not microbiologists, you can think about this way. Injury is like you get sick and you are in a nutritious medium, you kind of take a rest and then gain strength back and then start harming people again. So a lot of times when you are heat treating it, the bacteria get injured, but it doesn't die. But when you do the plate count, it may not show as a colony. You may think that it's died, but it's in reality it's still there, and with given time it's going to recover and then it's going to create harmful. So you have to use some proper medium to identify whether the bacteria is there or not there. And then we also assume that the process treatment is uniform. So when I say I'm going to process at 70 degrees Celsius in a big autoclave, you assume the entire autoclave is going to be at 70 Celsius. It's possible maybe this section here is 65, this section is 65, and then your rest of the section is 70. The bacteria in these locations can survive, then it creates a problem. So you want to make sure that if the entire section is 70, it's okay, you can have some region 75 Celsius or much higher temperature, but you don't want anything less than your 70 Celsius. So you're always going to process at the appropriate temperature or a little bit higher temperature so that you deliver your heat treatment. The thermal death time can be graphically plotted using this here. Logarithmic n versus time, this is 1 over d. D is your decimal reduction time. Now, some of us are with the chemical engineering background. You may prefer this form here. You use natural log ln versus time, and then you use the k, and then you kind of use this type of equation. So this is kind of coming from traditional chemical kinetics, whereas this comes from more traditional biology type concept, but they kind of talk about the same thing. And then these are an interrelationship between how the K and D are kind of related. So you can also, by this extension of this concept, you can say that how many log reduction, how much time it takes to get complete inactivation. So let's say you have a processed food. Can I say I completely inactivate microorganism in that processed food? Mathematically, you're never going to say that, because mathematically it's impossible to have complete inactivation. So it's going to take infinite time to achieve that. So you always pay attention. So you can say I achieved 10 log reduction, or I achieve 7 log reduction, and so on, rather than saying complete inactivation. Thermal death time is one step forward. Basically, it takes how much time it takes to destroy the population at a given temperature. So, basically, for example, if I have 10 power 9 organisms and then I want to reduce to 10 power minus 3, then I have 12 log reduction. Now, the question is, what is 10 power minus 3? So, is it 10 power minus 3, is it practically possible with microbiology? Generally, it is not practically do that in microbiology. It is more probability concept, which basically say that if I process 100 pouches, or if I process 1000 pouches, one of those pouches probably going to have a survivor. So, that is where that 12D concepts come in. Even though it may not be practically you can demonstrate 12D concept in a lab environment. It is more probabilities concept. Here it is just to give you some idea how the log reduction can be defined. So, let us say you have 10 power 5 population. If you reduce 1 log, that means you are going to have 90% reduction, then you are going to have left with 10,000, whereas if you have 5 log reduction, you are left with 1 bacteria, and so on. So, this is how the concept of 5 log reduction, 7 log reduction, all those things come into picture. Again, we can revisit this slide later on if you have questions on the d value concepts. So, in the US regulators, they define certain time, standard times as a pasteurization time. So, 7D reduction, 5 to 7D reduction, 12D reduction, and so on. So, we said d value is the decimal reduction time for certain bacteria. So, I have here milk, meat, canned food. Is this d value is for same bacteria, or is it for different bacteria? So, the answer is the bacteria you define the d value in milk pasteurization going to be different. We will talk about that later. It is called Microbacterium tuberculosis. It is a bacteria commonly found in milk. Whereas, in meat cooking, it may be a different bacteria, E. coli, O157, or some other Listeria, and so on. Whereas, in the canning, it may be Clostridium botulinum or Clostridium sporogenes. So, in other words, the d value concept, even though this is kind of 7D, 12D, everything is same, but the bacteria associated with each food product is going to be different, because the target pathogen and spoilage organism for each product is maybe different. So, you need to make sure you understand what those resistant characteristics, and then calculate your processing time accordingly. So, here I am going to just to give an example. If I have 10 power 6 viable microorganisms and you have 3 minutes at 250 degree Fahrenheit, how many minutes takes to reduce the population 1 viable cell? So, you can kind of do some of these calculations mentally and then get that, but again we will revisit these calculations later on when we do our math. What would be the final count if you have 3 million bacteria treated with 5D process and d value 5 minutes? So, you have d value is 5 minutes and you have 5D process. So, 3 into 10 power 6, and then you have 5 log reduction, that is going to reduce the population 3 into 10 power 10, and so that means you probably have about 30 bacteria left. So, a lot of these things are simple mental math, probably you can able to do yourself when you come across those things once you get the good understanding of the d value concepts. Now, I mentioned different bacteria are going to have different d value calculations. So, for example, E. coli, you will see that it has a D55 4 minutes. What this means is the decimal reduction time for E. coli at 55 Celsius, right. So, this is your temperature at Celsius is 4 minutes. So, if you increase the temperature to 60, this time probably going to maybe reduced. Whereas, if you reduce the temperature to 40 Celsius, this temperature may be different. So, you have to kind of pay attention to that. So, if you look at Clostridium botulinum D121, that is 121 Celsius, you are going to have 0.1 minute, whereas if you look at D121 for sporogenes 2.6 minutes. If you look at more heat resistant spore Sterthromophilis, you have about 4 to 5 minutes. So, each bacteria is going to be different. On the other side, you look at the chemical changes. For example, denature of proteins 5 minutes, whereas chlorophyll destruction it's going to even take longer, 14 to 350 minutes or 1 to 10 minutes and so on. One thing you will probably see here is for the same temperature, at 121, the microbes have more heat sensitive or easily inactivated compared to your nutrients. So, in other words, you probably, while some nutrients are heat sensitive, many nutrients are heat stable. So, you can able to process them even at high temperature and they survive the heat process, whereas you can able to inactivate them through heat treatment. So, that is something we have to compare. So, you always try to compare the food safety side and then the nutrition side to get some assessment. The d value is influenced by the composition. So, for example, there is an organism called P83679, which is the Clostridium sporogenes. If you do in a cream style corn, it has a d value about 2.47 minutes, whereas if you do in phosphate buffer, it is 1.31. So, a lot of times in the academic environment, we may be doing microplates using the buffer solutions, and then we expect that holds good in the real food systems. It may not happen. So, you need to make sure that you understand what the survival in the actual food product itself. The microorganisms also, the d value of the microorganism influenced by the type and strain, the composition, your pH and water activity. So, we saw earlier pH is an important factor which affects the survivability of microorganism. So, if a microorganism neutral pH and has a d value of 1 minute at 60 Celsius, if you acidify, then the d value may be go down. Instead of 1 minute at the same temperature, it may become 0.7 minutes or 0.6 minutes because it is an acid environment, or it may be completely even inhibited. So, you have to consider that. And then you also have to consider the agent stage of the cell growth, but normally when you are doing processing in an industrial environment, you may encounter what they call wild bacteria. So, that means these bacteria never come to the lab, it just stays in the nature, and they may have highly virulent characteristics. So, when you are an industry person, you always try to monitor those things and then make sure that your process is properly developed for that, and then at what temperature you are kind of processing. And this is a mathematical relationship which kind of help you to estimate the d value at any given temperature. So, the d0 is the target d value at your particular temperature T0, whereas this is your reference temperature here Tt. and the Z value is your thermal sensitivity of the bacteria, which we will talk in the next slide or in the coming slides. When you look at the D value, the increase in temperatures, you can kill more bacteria, so you can able to change the D value accordingly. So if you have a D value of 1 minute at 60 Celsius, you increase the temperature to 70 or increase the temperature to 80 or 90, the D value is going to go down. Instead of 1 minute, it may be 0.5 minutes or 0.1 minutes and so on. So you're going to have certain benefits. So normally, it's a known fact in the industry, high temperature short time is better because higher the temperature, you inactivate the bacteria quickly with the less time. At the same time, a lot of the nutrients are heat stable, so higher the temperature, it may not affect the nutrients that much. So you may have still a nutritious product, but less in terms of microorganisms. The next concept is the Z value. Because different bacteria have different sensitivity heat, some are more sensitive, some are less sensitive, we use the term Z value. Basically, it's the temperature range in which you're going to have a 10% or tenfold change in D value. So, if you plot your logarithmic D value versus the temperature, you're going to have certain change in the D value, that's your Z. So, normally it's kind of given for certain microorganisms. So, for example, Clostridium sporogenes, it's a Z value of 10 or 18 degree Fahrenheit. So, usually people kind of assume, particularly when you do canning, those kind of data is kind of calculated. Now, some of these concepts, D value, Z value, remember these are not modern concepts. These concepts were developed probably in the 1920s and 30s, and then still we are kind of using, adapting over time. So that means these are all tend to be a little bit more empirical. So there are certain terminologies people use and so on. So we kind of adapt some of those terminologies with time. And then with the chemical kinetics, we kind of try to take that biological concepts and then try to convert it into chemical concepts and so on. But still, people use both sides of the equation. So when you are talking about chemical reactions, you are going to use the term activation energy EA, and then the temperature T, and then your rate constant K and K0. Basically, it's the same similar equation we saw earlier for D value, which is relating your rate constant K with a certain temperature, certain constant value K0, and then activation energy, and then the temperature. The R is the universal gas constant. So again, the units basically consistent with the how the K values are defined and so on and so forth. So again, trying to relate the biological concept logarithmic D versus logarithmic natural log ln, you are going to get two separate relationship, and then from there you can relate activation energy and EA value using this concept equation here. So the point here is it's possible to convert the chemical kinetics into the microbial kinetics, vice versa. But I think these are in today's environment, a lot of these databases are readily available. You don't need to memorize many of the details. You need to know where to look for those information and then use it. So again here the Z value for bacteria, you can see the Clostridium botulinum, I said 10, but it's in the range of 8 to 12. Sporogenes 9 to 13. On the other hand, if you look at the destruction of diamine, 20 to 30, whereas denature of protein 5 to 10, enzyme inactivation 8. So, what this tells me is if I have certain log reduction of Clostridium botulinum, let us say like a, 8 to 12 means 10, you may have more enzyme inactivator under those conditions because the Z value is going to be 8. So, if you increase the temperature, you are going to have more enzyme inactivated as a result because they are more sensitive, whereas the botulinum is a little bit more stable. On the other hand, your time in destruction is 30. So, they are kind of relatively very heat stable. So, you are not going to make major changes in the time and value when you change the temperature from one to other. So, when you kind of try to evaluate your process design, you have to look at the key nutrients and the target microorganisms, and then try to kind of play around, how many log reductions of bacteria I need. I basically need certain log reduction because nobody want to eat bacteria containing food, but people are also willing to eat maybe less nutrition, but they don't want to have unsafe products. So, you kind of play a trade off. The next concept is the F value. So, the D value kind of says, okay, in my thing I have bacteria and I am treating certain temperature, and under those temperature what is the time it takes to reduce the population by 90%. The Z value kind of tells how different bacteria are sensitive to different temperatures. So, let us say that I have a raw product, let us say like I have a raw meat and I have 10 power 4 bacteria, and then let us say that I want to, so the A, let us say the initial population is 10 power 4, and then I want a final population 1, which is also equal to 10 power 0. So, the F value basically going to calculate what is the decimal reduction time for the bacteria, what is the logarithmic A and logarithmic B value. So, in this example, if I have a decimal reduction time of 1 minute, so then the F value is going to be 1 minute times 1 times log 10 power 4 minus log 10 power 0. So, that means 1 into 4 minus 1. So, you are going to have certain log reductions there. So, that is kind of how you kind of trying to calculate. So, you probably, so the units here is, this is in 1 minute. So, this is in minute. So, that means this value F value is going to be in minute. So, in other words, I have a certain population, I am going to reduce the population from one value to another value, how much time I am going to process it. So, in this case I may be processing about 3 minutes. So, that is your F value calculation. So, in this calculation I did not consider the temperature variation, right. I kind of assume that the whole thing happens, let us say this is at 70 Celsius. That means I assume my vessel is at 70 Celsius. But in reality, your process equipment, you are going to start with room temperature, and then it is going to take certain time to reach your processing temperature, and then you are going to cool it down. So, all those time, come up time, and then cooling down time, all those things we are not considering. We are just trying to keep it simple, and this is where the F value concept is kind of sterilizing value concept coming in. So, this is the equivalent minutes at a reference temperature. So, here just a worked examples, you can say okay, at 250 degrees Celsius, like you can say the Z value for microorganism is 18 Fahrenheit. This is normally used Clostridium botulinum 18 Fahrenheit or 10 degrees Celsius, and then basically it is going to say how many log reduction you need. If you have 250 is 1.16, you need 6 log reduction, then you approximately need about 6.96 or about 7 minutes. So you can able to do some simple mental maths. But here, as I mentioned, it doesn't consider the temperature distribution. It's going to, in reality, it's going to take some time to reach the temperature, and then you are going to have a heating period and you are going to have a cooling period. It doesn't consider. It always assumes I'm going to be at the temperature, say 70 Celsius all the time, but it doesn't come look the temperature to reach the 50 or 70 Celsius and then temperature to cool down, it doesn't consider. So then we are going to go next one, we'll come to that in a minute, but in the literature the F value calculations for different products are given. So for example, asparagus about 4 minutes, corn 6 minutes, loaf and so on. So somebody has done these experiments. So as I was telling you earlier here, somebody has done the experiments. So when they say F0, it may be 250 Fahrenheit, and they kind of put some of these different products, and then I estimated how much time it takes to get certain log reduction in different products and so on and so forth. So there are databases available in the US, what they call National Candidates Association. They have published books that has a lot of these data available for different food products and so on. So in other words, if you are a new person doing canning today, you don't have to start from ground zero. You can always look at some of those reference sources, and then you can look at your formulation, and then you can be able to develop your calculations accordingly. So the next equation we are going to use is this relationship here. Log Ft is going to be this here. So basically, when I have a canning equipment, initially maybe at 25 degrees Celsius, and then it's going to go to 121 Celsius, and then you are going to process say 30 minutes, and this come up time maybe, I'm just making some numbers, 15 minutes. Then you are going to cool it down maybe another 10 minutes. So how do I compare some of those values? So you can probably use this relationship here. So this F0 is basically your reference temperature. So if you are doing at 121 Celsius, then this is your lethality at that 121 Celsius. And this Z value is the Z value for your target bacteria, and then this is your temperature, and this is your reference temperature. So I have a one worked example I can show you in the spreadsheet the next once we finish this lecture, so you have a better picture of that. So essentially what we are trying to do here is, when I start here, I'm going to take this temperature history data, and then I'm going to divide this into smaller time segments. And then I'm going to look at, for each segment, how much accumulation of bacterial death happens. So in other words, when I start at 25 degrees Celsius, the temperature is very low. The bacteria may not have any death happening there. Whereas when I probably approaching close to 100 Celsius, it's going to have some lethal effect. So there's going to be some death happening. So I can consider that death. And then when I reach my target temperature, for sure the bacteria is going to die, and I can calculate that. And then when it's going through the cooling section, there's going to be some death happening as well. So in other words, the death of the bacteria when you are heating, cooling in an industrial environment can happen during the preheating side, during the cooling side, as well as cooling. And then you have to able to mathematically calculate using this relationship what is the total death happening at different stages. However, you don't want to take credit for bacterial death in all those time intervals, because you kind of want to do things much more conservatively, and you can probably able to calculate things accordingly. Normally, for Clostridium progenies and Clostridium botulinum, at 250 is the reference temperature, and your Z value is about 10 degrees Celsius. For vegetative bacteria like E. coli, Listeria, you use a reference temperature of 80 or 60 Celsius, because pasteurization is somewhere around 70 Celsius, and depending on the resistance you may use 80, 60, and then your Z value is between 6 to 9. So, these are all empirical values based on the industrial experience. So, this is kind of the temperature distribution curves I kind of talked about. The red one shows the temperature inside a canning retort, whereas the blue line shows a convection treated product. So, if you have a juice, it can reach the temperature of the retort quickly, whereas if you are processing some meatloaf or something, the conduction heating takes place. So, the come up time is going to be slow. You are going to have this longer come up time, and then you are going to have this cooling down. So, you have to accommodate these temperature curves in your mathematical calculations to get your total processing time. So, for that, basically you are going to take that curve and then divide them into small segments, and then you are going to assume what is the microbial lethality happening in that particular section and what time. So, let us say this is 1 minute interval, then I am going to calculate this as a 1 minute interval. If it is 1 second interval or 5 seconds interval, then your time is going to be different based on that time interval concepts. Then what I do is I kind of calculate the values in each segment and then kind of sum them up, so that you can get the accumulated lethality. It is a good idea to learn how to do this in by hand or with the computer by yourself as a student. Later on, when you go in the industry, you are going to have software available where you input certain parameters. The software is going to provide all those calculations for you, but it is always good practice to know the math, so that you can verify whether the computer is making any calculation errors and so on. The next one is the spoilage probability. The spoilage probability basically going to tell what is the likely that a product going to spoil. So, let us suppose you are going to have a bacteria where it is going to have total number is about your processing R. So, R is the total number of containers, and if you have a N1 as the initial population, N2 is the final population. So, based on this your F value calculation, you have certain decimal reduction time. So, initial population is R. So, each container has N1 population. So, you are processing R cans. So, R times N1, and then the final population is you are processing again R cans, and then population is N2, you have N2. If your probability of reducing that spoilage is to 1, then this become 1. Then from there rearrange the math, you can calculate R is 10 power F over D divided by N1. So, this can kind of help you to determine what is the likelihood you can have spoilage happening in a particular canned product and so on. So, you have in this example, you have a 2 into 10 power 5 organism per container, and you are processing for 45 minutes. Your D value at 118 is 3.5 minutes. So, here whenever it says you are processing for certain time at a specific temperature, that leads to your F value, because F value kind of tells you how much time you are processing it. And then D value is your decimal reduction time, and then your initial population is 2 into 10 power 5. So, it kind of provides that. So, 3 into 10 power 7. So, what does that means is, if you process 3.6 into 10 power 7 containers, one of them likely to spoil under those conditions. Now, as a processor, is this my acceptable risk? So, you can probably say, okay, I can use a milder processing. I can accept one container out of every 10,000 containers spoil. Then you can maybe reduce your spoilage intensity of treatment, or you can increase the intensity of the treatment so that I can have 10 power 7 containers, out of which one container spoil, or I think I'm making billions of cans every day in my factory. I don't want this much spoilage. Then you can increase this number to maybe 3 into 10 power 9 or some other value which is acceptable. So, each company, depending on whether it's a smaller or larger medium sized company and so on, the spoilage probability can be adjusted. Again, here you're going to have some mental math things. You can able to try to look at the processing time. So, again, one thing you have to look at some of these things is, when you look at these type of problems, before you try to get into math and solve the math equations to get the answer, think physically. So, in this example, I am processing a 121 8 minutes, Z value is 10. What is the equivalent minutes at 115? So, I am processing 115. Would you expect the processing time more or less? It's going to be less, right? Because you are going to process, it's going to be more, because you have 8 minutes, 8 minutes. So, 115 your processing temperature is reduced, so it takes longer to kill the microorganisms. Same way here. So, you probably go back to this equation here. T is F0 10 power 1 minus Z T minus T reference. You kind of use this type of equation, and then you substitute the values, and then you can do the calculations. F0 for a canning retort is 6 minutes. What is the equivalent minutes at temperature of 126? So, normally when canning, they assume F0 is at 121 Celsius. So, it's 60 minutes, 6 minutes. So, when you increase the temperature 126, so the processing time going to be shorter, because you're going to treat with a higher temperature. And then you can do the math. And then similarly, you have third example problems and so on. So, here are some solutions. So, 115 you have F value is 8 minutes, and your processing time 115 minus 121, Z value of 10. So, it's going to take a longer time to achieve the equivalent kill than a lower processing temperature. So, here's the solution for the next one at 6 minutes, and then 126 minus 121 divided by 10. So, you can have short time to achieve equivalent processing time. And again, this is just going to show you takes 10 minutes at 240, 250 it's going to be much shorter, 2.7 minutes. At 260, 10 minutes means 250, it's going to be much longer time, and so on. So, there are variety of these things you can probably try to solve yourself. you can use a calculator or you can use a spreadsheet for doing some of these calculations. So these are some selector reading materials. This particularly talks about the kinetics. In this lecture, I primarily covered the basics for thermal processing or heat treatment. The same concept can be applied to radiation, microwave, or Omi heating, pulse electric, high pressure processing, all those things. So this has an extensive review published in 2002. FDA kind of had a contract with number of people and they had a big review done. So this is kind of documented. So if you are looking at the new processing technology, this is a very useful information. And then you probably have some traditional kinetics relationship. So this may be on the book chapter or book material you may find useful. So with that, I think I will stop here and then we can probably have some questions and discussions. And remember, the reaction kinetics and chemical kinetics, these are the foundation for food processing, especially designing the safe food processing, whether you use thermal processing, non-thermal processing. The concepts we learned today, these are all extended by different things. So it's always good to make sure you understand these concepts.
During my MTech, so I go to visit to the industry. So they are mainly export the dehydrated item. You can see that's onion, garlic, or potato cubes. They reduce the moisture content about 6 to 7%. Then they irradiate. Also, then they go for the ozone treatment, and then they export to the US country. Sometime there is a microbiological issue, but because of that, the container will be totally rejected. After applying so many things, still there is a chance of microbiology. So which technique that you think they can avoid these problems? Because in entire year they can save more than 200 or 250 containers. Among them, 20 to 30 containers already rejected. Each every year, we still trying best technology during my internship. Still now we are facing the same chase.
Okay, sure. So is this a product? What's the product and what is the
Onion powder.
onion
And
powder? So this is raw material is onion powder,
yes.
and then it's treated by some dehydration.
Then they
Then
grind it in a fine powder, then
and
they
then it
sieve
goes
it.
through the
As per the sieve size, they simply market it. After they for adding calcium citrate to prevent the moisture migration, double layer polyethylene pouch, then irradiation as well as ozone treatment. Still now it is like
right. I think it's quite understandable they have the challenges because you are dealing with what they call low moisture content foods, and
yes.
basically these onion powders, they have water activity is very low. When you have a low water activity, then doesn't matter how intensive a treatment, microbes likely to survive in your product. So I think one of the simpler solution maybe try to have better control over the raw material quality. So in other words, I think have the supplier try to provide better quality raw ingredients so that you have less microbial load start with, then you're going to have better chance of reducing some of the microbial load. Because normally many of the processing technologies we talked today, these are all valid for high moisture content food. When the water activity becomes low and low, these techniques become less and less efficient. Even thermal processing, irradiation, and so on. So that means you have to use extremely longer processing time, and when you do that, it may affect quality adversely. So it's kind of the trade-off. So one of the better solutions is try to look at the ingredient suppliers. Can they able to have a better control over the raw ingredients so that maybe they can able to reduce that microbial load, then you have less issues.
okay, sir. Thank you.
have a very basic question.
Hmm?
How do we know how many log reductions we want? For that, do we have to know the initial load, microbial load? Like for example, if there is almond processing and there is some heat treatment that the almonds are going through, how do we know how many log reductions we want in that?
Right, sure. Yeah, that's a very good question, right? So I think the log reduction during different processing methods, whether pasteurization, sterilization, or low moisture content food type of things and so on, it all defined by the regulators. So in this case, I think I'm primarily talking about the US FDA or USDA type of thing. So they define 5 log reduction, 7 log reduction, and so on. Your question also bring in other interesting thing is how many log reduction is sufficient, right? So I may have a raw material which start with the initial population of 2, and then if I had a 7 log reduction, you may have 10 power minus 5 survivors. I may have a raw ingredients with the 10 power 4 population. If I had a 7 log reduction, then the population survival is 10 power minus 3. So essentially what we are trying to do is by controlling the initial microbial population, I'm kind of increasing my opportunity for reducing the food safety risk. So it's more of probabilistic concepts, right? So do I kind of, a lot of the major processes, rather than trying to get all the product and then try to process severely and then achieve reduction, they have quality control programs for the farmers or suppliers. So they tell, okay, I'm going to reject the raw material if the raw material's initial microbial population is less than or above 10 power 3 or 10 power 2. So they're going to have that, and then they are going to reward the farmers based on those numbers factors. So thereby they have a high quality raw ingredient in the sense it has a less microorganisms, so that they can also have better opportunity for retaining the product for a longer time, reducing the microbial risk, all those things. That's probably one way. Whereas if you have a raw product with a lot of problems, initially, then they may probably going to have potentially rejections, all those things.
Sure, because when they are using surrogate bacteria on, say, for example, like I mentioned, almonds, there is a set limit of those many log reductions that need to be achieved. So I was really curious to know from where they get that. How do they decide that that has to be the number of log reductions when they are using a surrogate?
Right. So again, you're introducing another good term, the surrogate organism versus the what they call target bacteria. So those of you who are not familiar with the term surrogate, so normally when you do food processing, you are going to use the bacteria like Clostridium botulinum or E. coli. These are all the pathogens. But in most of the industrial environment, they don't allow the bacteria, pathogens into the processing plant. So you have to use a non-pathogenic bacteria which has a similar characteristics as your target pathogen, and then you do those studies with that surrogate organisms. Then they are going to look at the resistant characteristics, and then what they do is they are going to look at historical outbreaks, right? So, in meat, how many log reduction, what's the common growth of spoilage organisms or pathogens, or in almonds, what are the things, and then they may decide, okay, approximately 5 log reduction is going to make the food safe. Whereas in some products, you may have to have a 7 log reduction to make the food safe and so on. So for example, in the case of apple cider, when you are picking apple from the tree and then you are making cider, the FDA sometimes allow you can also reduce the population by removing the microbes from the apple. You may get 1 or 2 log reduction, and then you may be using a UV treatment or heat treatment. You may get a 2 or 3 log reduction there, and then you can able to take advantage of combining this and that to get a greater log reduction.
Sure. So then they will have to monitor the initial log.
Normally, they don't do the initial log reduction,
Okay.
because if you try to do that in the industrial environment, it becomes a nightmare. Because today you may get a batch with a 10 power 3 population. Tomorrow you may get a batch 10 power 7 or 10 power 4 population. So the way to avoid that variation is you kind of make your supplier accountable. Okay, you are going to consistently give me 10 power 3 population. I'm going to do a quality inspection. I'm going to reject the batch if you're going to exceed that limit.
Sure.
So you're going to have that built-in safety mechanism, 7 logs. So that's your acceptable risk, how much risk you are willing to take. In the case of canning, you go to 10 power 10 or 10 power 12, it's higher risk, whereas in the case of pasteurization, it's relatively lower risk.
Thank you so much.
Mm-hmm.
Thank you.